So that brings us to the final discussion on improving accuracy by changing the basis functions. So when we talk about basis functions, there are broadly two classes, one are called subdomain and the other are called full domain. So what does this mean? The pulse function which you already saw, right? So the pulse was, right, it's 0 over here and 1 over here. So this basis function is non-zero only in a subdomain of the entire domain. It is not non-zero everywhere, right? That is why the word is self-explanatory, that is why this is called a subdomain basis function. Okay. So instead of a pulse, you can also do better, you can do, so this is like the Taylor series, this is the first term of the Taylor series, constant. The next would be linear, right. So you can have these triangular basis functions. So for example, this is one basis function, okay. The other basis function can be something like this, okay, and so on. So these are another class. So this is basis function A, basis function B, basis function C. So the way these are constructed is very clever again. The place where this guy is 1, the other basis function has a value 0. Similarly, you can see this function is 1 over here. My drawing is a little bad, but this 0 is supposed to come over here, okay. And similarly for this should match, okay. Yeah, so A is the first basis function, B is the second basis function, C is the third basis function, and so on. So if I, for example, let's just take basis function A and basis function B. Supposing I add these two basis functions, what will the result look like? So let's start from here and go all the way up to here, okay. So I'm adding A and B, right. So when I start from here, what will this function look like? B is 0, right. So this guy will go like this. When I come to this point, B is still 0, and now by the time I come over here, it's going to be 1 again. So this is going to be, I'm adding this guy and this guy, I'm going to actually get a line. You can see that these two curves, they are going to add to a constant, and then as I go down, it's going to follow this all the way to 0, because basis function A is 0 by now, right. I can extend this idea. Supposing now I do something like, basis function A as a function of y, let us not choose B, let us choose basis function A as a function of y, let us give it some value 1 and 2 times the basis function B, okay. So what will happen, how will this guy look? So this is where, right. So basis function A is like this, basis function B is like this, okay. Now I am combining these two basis functions, but with a different height. So what will it look like now? When I start from here, the value will follow along A, right. So it's going to be red like this, and this height is being forced to be 2. So how will it go from here to here? Straight line. Yeah, so it's going to be the value at this point of the function will be 2, because at this point FA is 0 and FB is 2, right. So I mean 2 times FB is there. So this guy is going to go up and then come down over here. So by doing this, what will you call these 3 segments? They are linear. So what I have done is I have replaced this function by piecewise linear approximation. So my function that I am approximating now is continuous. Earlier my function that I was doing expressing using pulse basis function was discontinuous. So I have now moved to a continuous basis function, but it's still not differentiable, right. It's not smooth, but it's better than pulse, okay. The only price you have to pay now is calculating AMN will require a little bit more work. Earlier my, in the numerator my g was just 1, so it was very simple to integrate. Now it will be a linear function, right. So you can extend this idea, you do not have to deal with lines, you can deal with half cosines, these can be your basis function. So, those are about subdomain basis functions. Finally, there are full domain basis functions, which as the name suggests, they are non-zero all through the line. Okay, any guesses for one very popular full domain? Cos or cosh. You've all studied it in first year of engineering. Full domain means it's non-zero everywhere in the domain, the basis function. Sinc is a more complicated, something simpler. What about combinations of sines and cos? What are they called? No, more complicated. What is the combination of sine and cos called? You studied in first year signals and systems. Fourier series, right? So, if I have some, I can write down my basis function as like this. So, I can say a naught plus n is equal to 1 to say capital N and cos k n y plus b n sine. You all have studied why Fourier series are very nice. They can approximate a function, a periodic function very well, blah blah, right. So, your basis functions now have become this cos and sine. Cos and sine are non-zero everywhere, and now I am representing them by coefficients a n and b n, okay, and there is of course a DC term that I have to take care of. So, if I know beforehand that my solution is going to look oscillatory, then why choose pulse basis function or piecewise linear? May as well choose the function, choose the basis function which I intuitively know is going to satisfy the, is going to be close to the basis function. By doing that, I will get away with a small value of capital N. If the actual solution is sinusoidal.
But if you put this into that GFY,
yeah.
you have the divided by root.
Yeah, the divided by root, the R term will remain as it is. Now, your numerator will have one function of y prime.
How will you integrate that? You have to
Gauss quadrature, Gauss-Legendre, any quadrature rule. I don't care what the function is. I just need to evaluate it at one point. So, more and more you will appreciate the power of a quadrature rule. You don't care what the function is, just evaluate it. Sine and cos is easy to evaluate, what's there, right. So, that's the strategy that we will use. So, this is also a bit of an art, choosing which basis function depending on the problem at hand. Okay. So, with this we can bring this particular introduction to integral equations to an end.